So yeah, thanks John for the introduction, and thanks to Daryl for making all the arrangements for me, and in particular recovering so smoothly when the train strikes were announced. And thanks to all of you for showing up. So I'm going to try and tell you about some connected bits of mathematics that are on the one hand very pure, they feel a lot like we're playing games, and on the other hand turn out to have enormous amounts of real world importance. And I'm going to try and squeeze in a couple of things I've done as well, but this is mostly not going to be about me. So let's start all the way back in the 1730s with the city that then was called Königsberg. It's now called Kaliningrad. At the time, it was in Prussia, it's now in Russia, and there's a river that runs through Königsberg. I'll call it Königsberg because it's up like that on the slide, called the River Pregel. And in the River Pregel, there are some big islands. And right in the middle of town, you can see these islands still now. If you look on Google Maps, you'll see there's a small island, and this one, D here, is a big island that effectively disappears off the edge of our picture here. And then this is the north bank of the river, and this is the south bank of the river. And people like to go for walks along this river. And apparently people went for walks on Sundays, and they would set off on a Sunday afternoon. And the question was, is it possible to go for a walk? So we're going to start somewhere, we're going to walk around, and then eventually we're going to get back to where we started. So starting and finishing in the same place, such that we cross every single one of these bridges exactly once. So if you look on a modern map of Kaliningrad, you'll see that quite a few of these bridges remain, but at this point there were 7 of them. So you can see 2 going up to the north bank from the small island, 2 going to the south bank. This one's called the Honeymoon Bridge and connects the 2 islands, and then there's a couple more bridges there. And so people tried, couldn't seem to manage it, and tried some more and couldn't seem to manage it, and had no real way to think about this question. Well, along comes Euler, who is a Swiss mathematician. He's a lovely chap. He's probably the most prolific mathematician of all time, is Mr. Euler. He published 866 papers, which is still an all-time record, and not all of them have still appeared in print. The collected volumes are still gradually appearing. He's probably most famous for an equation that some of you might have seen before, the one that says that e to the I pi is equal to -1, which is a beautiful topic for a talk, but is not the talk I'm going to do today. What I'm going to tell you about today was that Euler looked at this question, which had been asked for some time, and in 1736 came up with the answer no. And his answer no was the beginning of a whole new discipline in mathematics called graph theory, and also the beginning of another whole discipline in maths called topology. But I'm going to start with the graph theory bit. So let me start by telling you how Euler was able to answer this question. So what did he realise? Here's a picture of the islands. He thought about this problem and he realised that, well, for starters, the shapes of the islands don't matter. We don't actually care that this is a bank, that this is a smallish island, that this is a bank and that this is another island. We just care that there are 4 places called A, B, C and D. And we don't really care how you walk across A, if you go from this little bridge over to that one, or if you go from this little bridge back round on that one. We just care which bridges we use. So the shape of the island A doesn't matter, because the question we've asked is just, can we cross the bridges? We haven't said anything about whether you stop and dance a jig in the middle of the island on the way. So we can simplify this and just say, I'm going to have some dots representing the land masses. And so let me label them the same as they are on the picture here. Here's A, the little island in the middle. B is the south bank. C is the north bank. And D is the other island. And I don't need any more information other than that there's 4 of them. And actually, it doesn't really matter where I put them on the board. I've just put them so you can match it up. So their locations don't matter. I mean, if this island was suddenly magicked all the way down to here, it wouldn't change as long as I kept the bridges in the same place. So all that really matters is how many bridges link each pair of land masses. So going from A to C, I've got 2 bridges. Going from A to B, I've got 2 bridges. And then D gets 1 bridge to the north bank, 1 bridge to the little island, and 1 bridge to the south bank. And so all of the information in that complicated picture is actually here in this much simpler picture. And so now the question becomes, can I walk around this picture using each of the lines exactly once? So what I've just drawn for you is an object called a graph, so not in the sense of XY axes, any of you doing this at school. What we mean by a graph in this sense is a set of vertices. So those are the things that I've marked with dots. Those are my A, B, C, and D. And a set of pairs of vertices. So this is one pair, AC, a collection, and another pair, AC, and something joining A and B, and another thing called A and B. And I call those edges, that's what graph theory wants to call them, and we draw them as lines. And so let's think how Euler then answered this question, having made this simplification. Well, we want to go for a walk. So if I walk somewhere and then leave again, I can't use either of those bridges again. The rule is we're meant to use each bridge exactly once. So if I walk somewhere and then leave again, I'm going to use up 2 of the edges, use up 2 of the bridges. I cannot cross those bridges ever again. If I start somewhere, so maybe the island, or maybe the big island, or maybe one of the banks, I eventually have to come back there again. So that also has to use up 2. So passing through uses up 2, starting and finishing uses up 2, but there's 3 here. So whatever I do, I can't possibly use up just 2 there, right? I could start here, but then I have to use up these 2 and then I can't come back again. Or I could start somewhere else, I'll go through, use up 2, and there'll still be 1 left over that doesn't let me go in and out again. So it's not possible for me to go through all of them. So Euler invented this thing called graph theory. Now I should emphasize, as far as graph theory is concerned, this picture is a nice way of thinking about it. It's a really nice way of thinking about it, but it's not the graph. The graph is just A, B, C, D, and then these pairs, AB, AB twice over, AC, AC twice over, CD, AD, and BD. So the picture helps us think about it, but the graph itself is just some letters and some pairs of letters. Right. Let me tell you a famous problem in graph theory called the party planning problem. So I want you to imagine that we haven't just had an enormous pandemic, and or maybe that we have, and for this year, to make up for it, you're going to host an enormous family Christmas, like a really, really huge family Christmas, and you're going to have 100 people. And somehow you own some kind of baronial mansion where you're going to manage to sit all 100 of your nearest and dearest family members around a large table. And families being what they are, some of them don't get on. And what you'd quite like, I mean, Christmas is trying at the best of times, but arguments might break out if certain aunts and cousins are sat next to each other, and it would be much better if you could have them not next to each other, so that instead everybody can have a nice day. So your problem is find a table arrangement such that nobody's sat next to anybody that they don't like, such that people are only sat next to people that they can get to the end of the Christmas pudding / trifle / whatever your end of meal choice is on Christmas Day, without any fights having broken out. Well, we can model this problem as a graph. So if I make a picture like this one, where you have one vertex, one of these dots for each person, right? So our enormous 100 family Christmas, you'd have 100 dots to start with. And then you're going to draw a line between 2 people, so an edge connecting 2 people, if you think they will get through the entire meal without insults being hurled. And now, for Euler's problem, we wanted to walk across all of these bridges. Now our problem is that we want to seat everybody at the table. So instead, we've got this graph of people that can safely be sat next to each other, and I want to find a route all the way around it that includes each person exactly once. So nobody's missed out from the dining table, and nobody has to suddenly jump between courses and go and sit somewhere else to talk to somebody else. They're all in one seat, and they do have a seat. So we want to find a route around this graph that visits each vertex exactly once and returns to the start, because it's a big circular table. Well, it turns out that doesn't sound very different from the one I put up there. And Euler came up with a complete solution to this problem, not just the one that I showed you. Turns out this problem is extremely hard to solve. So I once talked about this problem in our time, and I got an email afterwards from somebody who works for a company with a website called perfecttableplan.com. And it exists. I checked again today. It's still there. And they sell software to help solve, I mean, presumably not family Christmases. But he mentioned that the biggest one that they had solved So it gets hard. 100 guests would be really hard if lots of them didn't get on. If you didn't have very many roots around, that would be difficult. The largest one they'd managed to solve had 4,000 people at it, but in different tables, not one big table. But he said they had 3 rules they had to satisfy. One of them was absolutely hard and fast. Husband and wife had to be sat side by side. One of them was a strong preference, which was that people who attended the same synagogue sat together. So I'm not sure what the event was, but people from the same synagogue had to sit together. And then there was a weaker preference that if possible, people from the same state should be grouped together onto tables. And they were allowed to violate both the synagogue and the state rule if it got too complicated. And he said it took several hours to find a solution, even with being allowed to break those things. So this is a genuinely hard problem, and people make a living out of solving it for people. But it's actually got quite a long history in a slightly different guise. So it's started, this problem is called the Hamiltonian circuit problem, and it goes back to the Irish mathematician William Rowan Hamilton. So he's most famous for, well, all sorts of things. My personal favourite is the stuff that he did in algebra, because I do algebra. But he, at one point, thought he was going to make his fortune with a puzzle that he invented. Now, this isn't the exact original puzzle, is my understanding. It's a kind of replica of this problem. The original puzzle was a shape that looked a bit like a globe, and you were asked to try and find a path around this shape which visited every one of the corners exactly once. So let me draw this up for you. You maybe can't see it quite so well. So it's reasonably complicated. So what we've got is a big outside pentagon, and then in the middle there's a smaller pentagon going the other way up, and then each of these is attached to a vertex, and each of these is attached to a vertex, and then these 10 are all joined up together like that. So this is a picture of this, which you maybe can't see quite so clearly, but I've just redrawn it. And you can see the pegs here, and some of them have been put in, and so the question was, can you find a root around this sequence of dots that visits every vertex exactly once, so visits every dot exactly once and returns to the start. Now, Hamilton thought that this was going to be an amazing puzzle, and that lots and lots of people were going to buy this puzzle. And they didn't, and let's see if the reason is that we can actually solve this right now between us with not too much effort. So I'm going to start us off and suggest that we quite lazily go round the outside. We have to visit those vertices. What could we then say about continuing from here? Where do we then have to go? Anyone going to be brave? What do we have to do? We want to visit every single place exactly once and eventually get back to where we started. So what has to happen now? Yes? We have to go in. Thank you. So from both of these, we now work out that we have to go in. And now we look at this one, and well, we're going to have to get both into it and out of it, right? So one or the other of these had better go into it. And at the moment, this whole picture is completely symmetric, so it shouldn't matter which one I pick. Right? I could reflect this right down the middle and it would look the same. So let's say that this one's going to come into here and then come down again. All right, well, what more could we do here? We need to go round all of these vertices, so why don't we send this one just right the way around the outside here to here. Can anyone see how to finish it off? Yes, exactly like that. So we go in, and then we go round back the other way, and then we're back to the beginning again, and we've made a complete circuit that features every single one of those dots. Now, I don't know about you, but I wouldn't want to spend lots of money on a wooden puzzle that I could solve that easily, and that once solved, what are you going to do? I mean, you could try and find a different route around. So Hamilton did not make his fortune with this puzzle, but it did mean that trying to find roots like this became known as the Hamiltonian circuit problem and are still named after him, and he would probably be kind of sheepish that he's got such a problem named after him, as he's got fancy things named after him too. Now, the interesting thing, though, is that quite small changes would make this thing unsolvable. So although we found a solution to this quite easily, it wouldn't take me changing the graph very much at all for there not to be a solution. And that's one of the things that in some sense makes this a difficult problem to solve. And I'm going to come back to this problem in a few slides' time, but I'll leave it just like that for now. How would we solve hard problems like this? Well, I've already mentioned with the party planning thing, we solve them on computers. So let's let the machines come in that will help us. So here's Alan Turing, probably most famously known as the person that did the Enigma machine, breaking the codes during World War II. But actually, I'm more interested in the stuff he did earlier than that. I'm interested in stuff he did in the 1930s. So we're going to be talking about what are called decision problems. So using computers to answer decision problems, that sounds really fancy. It's not. It's just a problem with where the answer is yes or no. So you need some kind of well-formed problem where the answer is either yes or no. So can I walk around this using each of these edges exactly once? We worked out the answer was no. Can I walk around this using each of the vertices exactly once? And we worked out the answer was yes. So both of them are good examples of decision problems. The answer is just yes or no. So Alan Turing proved in 1936 that there exist decision problems which can't be solved on any computer. So nice maths-sounding things where the answer is yes or no, where you're not going to be able to write a computer program which can always solve them. How did he do that? Well, he did it by in particular showing that no computer can test whether a given program is going to stop. So I've got some program that I've written in Python or something, and I've got some possible input to it, and I want to design a master program that no matter what my Python program is, says if it'll stop on that input. Turing proved you can't do that. So you might be able to test whether a particular thing is going to stop, but you can't write something that will test whether everything will stop and say yes or no, or whether it will run forever. And this really had a groundbreaking effect on mathematics, and would be another lovely talk, but is not the talk I'm going to give today. But let me just mention, for those of you that know a little bit more mathematics, once you know what Turing's done, it's quite easy to prove that in fact there's uncountably many problems where we can't get an algorithm to say whether the answer is going to be yes or no, and only countably many decidable ones. So in some sense it's quite unusual to be able to solve problems, unfortunately. We'd quite like it to be the other way around, but it turns out that it's unusual to be able to solve them. And there are all sorts of very, very practical, real-life ways in which this can affect us. But I thought I would just mention that, for example, it's impossible to decide whether a player has a winning strategy in that famous card game, Magic the Gathering. So this is something where you trade cards amongst each other, depending on attributes. And genuinely, it's not possible to decide whether somebody's got a winning strategy based on the original cards. But all of the ways in which these things come up, it's talking about stuff running forever. So infinity somehow has to sneak in there for running forever to be possible. You couldn't run forever unless you had a bug in your code trying to answer this question, because it's very finite. There's only finitely many ways you might be able to explore the thing. So on some level, you're never going to run forever. These problems are solvable on computers because they're not infinitely big. So although I would love to talk to you about undecidability, I'm going to move fairly straight on and say the things I'm talking about, we definitely can solve on a computer. They're not too big. But even if something can be solved, it's reasonable to ask, is this going to run quickly? Is this going to take forever? Or is it somewhere in between? So how long should I expect to find to wait for an answer to this problem? So for example, if I wanted to just add those two 3-digit numbers, and even taking account of carries, that would be 5 single-digit additions, even if you're really, really rigorous about tracking exactly where the carries are. I add 3 to 9, and I get 12, and so there's an annoying 1 I need to hold on to. There's a 2 and a 7 giving me a 14, with another annoying 1 I need to hold on to. The 1 and the 5 is going to give me a 6, and then I need to do the +1s from the carries. Okay, so roughly speaking, it's taking something related to the number of digits we're talking about, roughly. Right? I added each one, and then I had a few more for carries. Multiplication's a little bit worse. So if I wanted to calculate that, it depends exactly what order you do it. But the 9 single-digit multiplications, I'm quite clear on, you're probably going to multiply each of the bottom 3 digits by each of the top 3 digits, and then the order in which you choose to do things will affect how many additions you do. So I rigorously stuck at single-digit additions, and the order I did it came out to be about 14. But the important thing here is this is roughly 3 times 3, because I needed to multiply each digit by each digit. So this is a bit harder. This was like the total number of digits, and this is the product of these things. Okay, so it's a bit harder, but still not too difficult. Any of you who've got as far as doing linear algebra and have learned how to multiply matrices, you get your matrices and you slide something over another and you multiply the matching things and then add them. So the way you first get taught to do this, if they've both got n rows and n columns, you're going to do about n cubed products and then a whole load of additions. But that's just the way you're first taught to do it. So there's a whole industry of people trying to find faster ways to do it. And I think the most recent one, Mormon and Williams showed in 2020, so really quite recently, that there exists some number c, they don't work out what c is, it doesn't really matter, such that c times, so this was n cubed is the obvious way, you multiply each row by each column and then add them up, and you've got n squared times you have to do that. They managed to get the 3 down to 2.3286. And I was glad I'd checked, because I had given a version of this slide once before, and at that point it was somebody else's name and the date was 2014, and that 6 there, the end 6, that was a 7. So people are making progress on improving these things, and they care about improving these things, but it's going to take quite a long while until it's got down to 2, which is what people are wondering if it might be. So the first way you learn to do things may not be the fastest way. So I'm going to take a very, very broad brush. I'm going to think of all of these as actually being quite quick things to do. And the class P, that's a special font on that P. It may look like a normal P, but trust me, it's a special P. Is all decision problems, so yes, no problems, that can be solved in time that's bounded by some polynomial of the input size. So I'm going to take a very, very rough cut. So this was kind of like the sum of the input lengths. So that's basically, it takes about as long to solve as you have to type in 6 digits, and it's going to take a comparable number of steps to solve it. Here you type in 6 digits and it's taking 9. Well, it's certainly taking no more than the square of 6 steps to solve it. Here you put in n squared and then n squared, and it's taking n cubed to solve it, so that's your original thing to the power 3/2, so that's a polynomial. I'm allowing much bigger ones than that. Why am I being quite so lazy? Well, here's an n. Let's compare quite a big polynomial. So I haven't shown you anything that takes n to the 5, so that's number times number times number times number times number, 5 of them all lined up, multiplied together. That's a big polynomial. And here's 2 to the n, which is like the smallest thing you might think of that's not polynomial. And let's imagine that you're running on a computer which can do 1,000 things per second, let's say. So you put in something of size 2, just like a little problem that you specified with, say, 2 digits. Well, the n to the 5 thing, it's going to take 32 milliseconds, if I'm saying it takes 1 millisecond to do each thing. And the 2 to the n thing, oh, I said polynomial time was going to be the quick ones. Well, for really small, polynomial time doesn't actually mean anything very much. So problems of size 2 aren't big enough to be meaningful. It's actually quicker to have an exponential algorithm at that point than this particular bad polynomial. Let's try something a bit bigger. 10 is quite a bit bigger than 2. Well, 10 to the 5, and then go from milliseconds to milliseconds. I'd be waiting 100 seconds for the answer on my computer. 2 to the 10, however, is, well, it's still slower. We're talking really big before these things start making a difference. Let me go up to 30. Okay, that's definitely bigger. N to the 5, how long is that now going to take to solve? 6.75 hours I would be waiting, so that's more time than... My definition of how long I'm willing to wait for my code to run is the time it takes to go and get a cup of coffee. And it does not take even me 6.75 hours to go and get a cup of coffee. Well, let's see, have I finally picked a number big enough that my exponential time algorithm maybe is going to take at least the same amount of time as it? Well, my exponential time algorithm is now taking 12 days. So although this started out looking like I would have been best, that this was too vague a description to say polynomial time is good, not polynomial is bad, by the time we're at 30, it really is making a difference. And 30-digit numbers aren't very big in the grand scheme of things. I mean, your credit card's probably got 12 digits on it, right? So 2 and a bit credit cards. And by the time we're at 100-digit numbers, well, the polynomial time algorithm is taking far too long for anyone to care about, but the exponential time algorithm is taking comedically long. So at this point, we really do think, okay, there's a worthwhile distinction to explore here between polynomial time and not polynomial time. So let me tell you about a problem I actually indirectly worked on. So I've mostly always been a very pure mathematician, but I spent a brief while in comp sci, and we was in a research group that solves the kind of problems I'm about to tell you about, and the more practical people in that research group did actually talk to the NHS about how to solve problems they cared about. And one of them, which I didn't personally work on, but still, was to do with the hospital rosters. So imagine you're running a large hospital, and each individual ward needs a certain number of staff, and they need to be certain grades. So you'll have some porters, and you'll have some junior nurses, and you'll have at least one ward nurse on at any given point of time, and there'll be junior doctors and consultants and so on. And of course, those people are real people who need to have lives and sleep and eat and things, and so they work some specified number of hours a week. And after working, you can't be like, oh, your next shift starts now. You're working, 40 hours this week in one batch. No, that's not allowed. It has to kind of have some gaps. We used to do that to junior doctors, but not quite so much anymore. So after working, people do need time off again. And so trying to work out how to schedule your staff to work in a hospital is a genuinely difficult problem. So suppose, for example, we had a minute little hospital, and I was going to try scheduling just by blindly trying each one until I found a successful roster. Well, even if I had, say, 42 shifts to fill and only 10 people to fill them, which would be a tiny little hospital, if I tried all possible ways of jamming 10 people into 42 shifts to see if one of them was a good roster, I would wind up with 10 to the 42 possible rosters. That's a 1 with 42 noughts after it, and is a very, very, very big number. All right, so we're not going to do that. What are we going to do? We're going to use a technique called backtrack search. So what does backtrack search do? It says that you work through the shifts, so start with Monday morning, first shift, and you consider each shift one by one, and you just try assigning the staff in order. So I'm going to start by putting junior doctor number 1 into shift 1 on Monday, and then my next shift will also be shift 1 on Monday because I need, say, 3 people on at that time. And the very first thing I'll do is try and put junior doctor 1 into that shift as well. And then I'll go, oh, junior doctor 1 can't be 2 people simultaneously. Junior doctor 1 is 1 person. I can't fill both posts. So what do? I just undo the most recent one and say, okay, I'm going to undo putting junior doctor 1 into shift 1. I'm going to put junior doctor 2 into shift 2 and continue. Sounds very simple. It turns out, once we've tried everyone for that shift, so suppose I've now tried putting, I'm halfway through because I would manage it for Monday, but suppose I've literally just tried putting everybody into Wednesday afternoon's shift, and every single one of them either hadn't had a long enough break or didn't have the right skills or whatever, then I stop looking at Wednesday afternoon and I start looking at Wednesday morning because I must have done something wrong by there already, and I should change what I've done there. So that's the basic idea of backtrack search. I just go through assigning things one by one and undo them, and undo lots of them if it turns out I've got myself really stuck, and stop when I get to a satisfactory roster. Well, it turns out this really is how we solve these problems. We do a mixture of this and reasoning about where we are, and it's a whole industry developing rostering things and stuff, but this is the basic idea. It's normally much quicker than testing all possibilities, that 10 to the 42, but you can actually cook up instances where it takes exponential time. So it's what we do when we haven't got anything better to do, and there are lots and lots of really clever backtrack search algorithms that are much better than what I've shown you, but this is the basic idea. But it still takes exponential time. So problems that we only know how to solve by backtrack search are hard. If we have no way of solving them other than backtrack search, they're difficult. So I had symmetry in my talk. I told you something about complexity. There was also the symmetry bit, and John mentioned symmetry. So let me tell you just a little bit about symmetry. Roughly speaking, it's a way of rearranging a thing so that when I've finished messing with it, you can't tell I touched it. So, for example, if we look at this graph, there's another picture of it up there. If I were to go, I don't want the one down the bottom to be B, I'm going to call it C, and I don't want the one at the top to be C, I'm going to call it B. And then I told you that my vertex set was A, B, C, and D, and I told you that my edge set was A, B, A, B, A, C, A, C, and then each thing with D. Well, I've just told you the same thing as I did before. I've messed with it, but you can't tell. If I had taken this whole picture, ignoring the red stuff, and rotated it by one click, you wouldn't be able to tell that I'd done anything. So swapping B and C would be a symmetry of that graph. Rotating by one click would be a symmetry of this graph. So yeah, in here we can swap B and C. What can't I do? Well, I can't swap A and D because there's 5 bridges going to A and only 3 bridges going to D. And so if I swapped them, you'd see 3 there and not 5. So things I can't do are interesting to work out as well as things I can. Here, it's quite hard to see things I can't do. Right? This is all 5s. Everywhere you look is 5s, because actually this is a very nice object. But things I can't do, for example, is take these 2, put my finger on this one, leave it where it is, and move this one round to there. Because this was next to that one. So if I send it round to there, it's not next to that one anymore. So that's a symmetry that I can't do there. Good. So coming back to my easy one, I can swap B and C. Can't send A anywhere, can't send D anywhere. I can also leave it alone. I tell you that I've messed with it, but I haven't actually messed with it. So that's got a special name. That's called the identity automorphism. That's always a symmetry. So this is the kind of things I mean when I'm talking about symmetries of graphs. I'm not going to give you a formal definition, but it's some way of shuggling the thing up so that if I just gave you the description of the graph afterwards, you couldn't tell I'd shuggled it. So if a set of symmetries is closed under composition, which is a fancy word for saying do one of them and then do another one, and inversion, which is undoing them, so symmetries are always undoable, but if I keep the undo symmetry in my set of symmetries as well, then it forms a group. There you go, that's quite a lot of first-year algebra. So I'm particularly interested in sets of symmetries that form groups, and in most situations they do. So for example, if I've got some graph and I consider all symmetries of it, so we've just worked out for this one, the only things I can do is swapping B and C and doing nothing at all, there's just the 2 there, that always forms a group. Because I said take all symmetries, and since undoing is always a symmetry, I'm always closed under inversion, and since doing a symmetry and then doing a symmetry is the same as doing a symmetry, I'm closed under composition. And it's got a fancy name, it's called the automorphism group of G. I'm only putting that up there in case I say it by mistake, so don't worry too much. But that is the name of the symmetries of a graph. So let's come back to my hospital problem and see how we might use symmetry to try and speed things up a little bit. So imagine I have 2 nurses, and they're of exactly the same grade. They're both, I don't know, grade D, let's say, that's an NHS grade, and they work the same number of hours a week. So they both do, I don't know, 36 hours a week. Well, if I've made a roster that's broken, and it features these 2 nurses in, there is no point swapping their shifts over. It will still be broken. If it was broken with nurse A and B one way around, it's going to be broken with nurse B and A the other way around. And it won't break a correct one. So there's no point spending lots of time deciding which one of them is going to do which until you're right through everything, right? So once I've started assigning them some shifts, then it matters who's who because they need their breaks and things. But in general, until I've started doing things, I don't want to treat them as distinct. Similarly, if assigning 2 junior doctors to work at the same time on 2 different wards broke a roster, so one of them's in Ward 1 and one's in Ward 7, and that was a bad thing to do, then if instead I'd taken the same 2 junior doctors and put them in Ward 7 and Ward 1, so same shift, opposite wards, that wouldn't fix it either. So there's some symmetries of the wards, potentially, and there's also some symmetries of the staff. So avoiding spending time looking at those, I'm going to try assigning someone to a shift and see if it's okay. If I can stop in advance and go, there's no point even trying that one, that's going to look the same as something I've already tried which didn't manage to do the rostering. It's called symmetry breaking. And it can make the search much, 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 much faster. So if you're in a situation where you've got a huge number of staff who are all on the same grade, working the same number of hours, you really don't want to be spending lots of time, first of all, to try assigning them one way around, then assigning them a different way around. So we proved back in 2006 that if your symmetries for your scheduling problem, say this nurse shuffling problem, all form what are called value symmetries, then we can break them in polynomial time. So we can quickly make our backtrack search problem still take exponential time, but be much faster exponential time. And that can be the distinction between can you run this thing and can you not run this thing. Let me talk a bit more about complexity, though. So I've talked about class P. Class P is the things that we can solve in polynomial time, and that's the things that we think of as quick. So working out if I could walk across all the bridges, we can solve in polynomial time, and adding things up, we can solve in polynomial time. NP doesn't mean not polynomial. I will shoot any undergraduate that gives me not polynomial as the definition, despite the N, but it sort of maybe possibly does, depending on the answer to a very big question. So a problem's in NP if it's easy to check a proof that the answer is yes. That's a slightly weird thing to get your head around, so let me give you some examples. So for addition of numbers and multiplication of numbers, a proof that the answer is some particular value, so I need to turn it into a decision problem, so it's a yes-no thing, so it's like, do these add up to this? What does a proof look like? Well, I might as well just do it, because I can just redo the calculation. So since I can do the whole calculation in 0 time, you don't need to give me a proof. I will just solve it from scratch. So any problem that I can solve from scratch in polynomial time, you can give me an empty proof, and I can just redo it. It's fine. How about things where there isn't a proof? So factorizing a number into primes. I give you some big number, 1001, say, and I say, can you please factorize that into primes for me? So numbers that are only divisible by themselves and 1. Well, if I tell you the answer, you can multiply them together and check that it's right. If I tell you this number is not prime, here are the factors, you can check. But if I don't tell you the answer, we don't know of a way of doing it at the moment that's efficient. And that's what the whole of internet security is based on at the moment. That if I give you a number and I go, what are the prime divisors, it's kind of hard for you to find them, at least if I don't make it even and divisible by 3 and things. If I make it so that it's only called big prime divisors, that's hard. But if I give you the prime divisors, you can multiply them again. That bit's easy. So it's one way difficult. The party planning problem that we started with. So I commented that it's really hard to find a way of getting people to sit around a table without fighting. I mean, that's true in life in general as well as in mathematics. But if I give you a seating assignment, you can quite easily check that nobody's sat next to anyone that they hate. So if I say there is a way of assigning this table and here's a proof that the answer is yes, you can. I may not have a proof that there's no solution. I may just be able to say, look, I've tried and tried and tried, and I can't find a way of ensuring that your Christmas is non-argumentative. I don't require a proof for a no solution, but if I can give you a proof for a yes solution that you can test, then it's in NP. And hospital rostering, so the shuffling of the nurses. If I give you the roster, you can check that it's all okay and that nobody's working too many shifts back to back, but finding a roster, I don't know. And if there is no roster, I have no proof that there is no roster, other than looking at them all and going, I couldn't find one. So I want to be able to check a proof that the answer is yes. Not that I can make a proof, but that if some angel gives me a proof, I can check it. So for many problems in NP, we don't know a fast way of finding the answer. So this one we do because I can do it from scratch. This one we don't, I believe. Somebody might shoot me if that's not true. This one we don't know a way of doing, and this one we don't know of doing. But we do know a way of checking when the answer is yes. For lots of these, so not factorization, but party planning and hospital rostering, the best practical approach is this backtrack search stuff that I've been talking about. Right, so here's the $1 million question. So in 2000, the Clay Mathematics Institute chose 7 of the most important unsolved problems in mathematics. So those of you that are young aspiring mathematicians, these are the things you should be thinking about, and offered a prize of $1 million for the solution to each of them. So only one of them has so far been solved, and one of them is P equal to NP. So if the solution is easy to check, so if it's possible, given a solution from an angel, for me to check that it's a valid solution to a yes instance, is it actually easy to solve the problem? So if the solution to the problem is easy to check, is the problem easy to solve? Now this is a big open problem, and I'm not directly working on anything to do with this big open problem, so let me tell you about some stuff that's a bit closer to things I care about, which we're hoping will shed some light on it. So back to graphs, because graphs are a good model for lots of these. So the graph isomorphism problem sounds kind of fancy, but it's not really. It just asks if 2 graphs are the same, maybe with different names for the vertices. So, for example, here's one. It's got 8 vertices, which we've labelled A, B, C, D, and G, H, I, J. I don't know what happened to E and F, but they ain't there. And there's another one, and they're numbered 1 to 8. And so the question is there some way of replacing the names on these with the numbers 1 to 8 so that the edges are the same in both graphs? Right? Are these the same graph, just with different names, and I've moved them around on the page differently? And if you stare at it for long enough, and you aren't colourblind, then you might well spot that the colours are actually giving you a way of seeing that these are the same graph. So it's saying A here is blue. If you look at the blue one, it's next to green, red, and orange. If you look at the blue one, it's next to green, red, and orange down here. So if you send each colour over to the other colour, those are the same graph. They don't look like the same graph, but they are the same graph. So this is in NP, and I basically just told you why. If I tell you what letter corresponds to what number, like I just did, the colours are telling you, then it's pretty easy to check that it's actually a matching that's correct. Right? So given a proof that the answer is yes, you can check it. It's not believed to be one of the hardest problems in NP. And this is where things get interesting, because if it's not one of the hardest problems in NP, and P is not equal to NP, then it should be not polynomial, but probably not exponential either. It should be somewhere in between. And so the question is, how hard is it? So let's look at some easy and hard cases and do some reductions. It turns out that deciding if 2 graphs are the same is an equivalent problem, I was going to tell you why, but I'm not because I'm out of time, to finding all the symmetries of one graph. So here's a graph. It's a little bit like this one, but it's only got 10 vertices to make life easier. Finding all the symmetries of this one looks reasonably fiddly. So there's some that you can see. You can rotate round the 5 and keep the 6, 7, 8, 9, 10, and you can reflect in various other places as well. But there's actually quite a few more symmetries than that, and trying to find them all by hand is a little bit painful. This one, though, if I ask for all the symmetries of that, well, that's nice and easy. I can do anything I want to those 3, but they have to stay amongst the 3 of them, and I can flip those 2. And what I do to those 3 doesn't tell me anything about what I do to the line below. I can do stuff completely independently. And then down here, well, obviously 10 has to go to 10, but again, I can do whatever I want to 6, 7, 8, and 9 freely. So what was it that made this one quite hard, and I didn't even try and list all the symmetries, and this one I just described every single thing you can do to that quite quickly. So things that make it easier is if the graph component is the fancy word for the bits that this has fallen into. So this is in 3 bits. And if I want to find the symmetries of this, I find the symmetries of each bit. Easy. If 2 bits looked the same as each other, I could also swap the bits over. It's also easy if some of the vertices have more edges than others. So down here, 10 had 4 things next to it, and 6, 7, 8, and 9 only had 1. So I had to do things to 6, 7, 8, and 9, and 10 just had to stay there. So that made my problem much, much easier. So in the 1980s, Lux showed that for graphs where we've got some given number, so each vertex has no more than, say, 7 neighbours, then I can solve the graph isomorphism problem in polynomial time. The problem is that the number of neighbours is the power in your polynomial. So as the number of neighbours, roughly speaking, so as the number of neighbours grows, the polynomial gets bigger and bigger and bigger. And he reduced down to exactly one family of hard cases, which is where the symmetries form what's called a primitive group. The symmetries of this form what's called a primitive group, which is why it's a hard case, even though there's only 10 vertices there. So we've got some sense that graph isomorphism shouldn't be insanely hard, but it might be not polynomial. Well, there was a really big breakthrough a few years ago now. So if P's not equal to NP, then these easier problems, or believed to be easier problems, because all of this is dependent on P not being NP, the easier problems that are not polynomial should be solvable in some time that's bigger than polynomial but smaller than exponential. And a good class to consider is what's called the quasi-polynomial functions. These are going to look a bit painful, but trust me, they're bigger than polynomial and slower than exponential. So this is things that look like 2 to the power, but exponential would be 2 to the n. This is 2 to the log n to some power. So it's smaller than something like 2 to the n, but it's bigger than polynomial. 2 to the log n is n, right? So that's polynomial. 2 to the a log n, so if I set b to be equal to 1, is n to the a. So that's polynomial. But 2 to the something to the log n to the b is not polynomial. And you fix some a at least 0 and b at least 1. Well, Babai showed in 2016 that there exists some constants a and b, such that graph isomorphism on graphs with n vertices can be solved in this quasi-polynomial time. He didn't work out what a and b were, he just said they exist. So he showed in particular that graph isomorphism is something that's worse than polynomial, but better than exponential. And then Harold came along shortly afterwards, Harold Helfgott, and showed that in fact you can take this power here to be 3. Now if that power was 1, then this would have shown that graph isomorphism is in polynomial time, which we think it probably isn't if P's not NP. So it was interesting that it's not much bigger than 1. It came out to be 3. So then I was able to use that to solve a problem that's harder than graph isomorphism in a special case. So the normalizer problem is a question in group theory. We're given 2 sets of symmetries, so permutations of the vertices of some graph, say, and I want to find what's called the normalizer in H of G. So don't worry if you've never met a group before, it's some subset of H. I want to find this special magic subset of H. And we're going to bound the time to do so by a function of n, so the number of vertices if it's the symmetry group of a graph. We know that it's at least as hard as graph isomorphism, and if it's in P, what do I mean by at least as hard? What we know is if I can solve the normalizer problem in polytime, then I can solve graph isomorphism in polytime. So we know that it's at least as difficult, and we believe it's probably a bit harder. Best known general bound is very recent. It was done by Daniel Wiebking only a few years ago, and that's time 2 to the n. But here's Sergio, looking very pleased with himself, is what I did with a young postgrad called Sergio back in 2020, just before lockdown. We showed that if you take this problem, which is believed to be harder than graph isomorphism, and you put a restriction on one of your groups and say that it's primitive, which is these funny class of groups that Lux mentioned before, then this is exactly the same function as Harold had. So we can solve this believed to be harder problem in the same function as we had for graph isomorphism, but we are doing a special case. It's an important special case. Right, that would have lost some of you. If you've just spaced out for a minute, it's about to get easier again. So let me finish by telling you how to win $1 million, because I figure you need some reward for having come to this talk. So how can you win $1 million? Well, there's obviously 2 ways to win $1 million. The question says, is P equal to N? But there's more ways than that, but I'm only interested in P versus NP. So there's 2 ways to win $1 million. Suppose you decided to try to win $1 million by proving that P was equal to NP, that the answer to the question, is P equal to NP, is yes. Well, you want to prove that if a problem is quick to check a yes solution, then in fact you can always find that solution. It turns out, and again this would have been a lovely talk in its own right, that all of the hardest problems in NP are equally difficult. So if you can find a way to solve a single one of them in polynomial time, of these hardest problems, then you prove that P is equal to NP. And I've shown you an example of one of them. So yeah, all you need to do to show that p is equal to np is to find a polynomial time method for solving your favourite one. So you can look through this huge list of them and just pick your favourite one and find a way to solve it quickly. And one that appeared in this talk is the party planning problem. So if you can find a way to seat people around a dinner table for Christmas such that people won't fight in polynomial time, you can win $1 million. Little word of warning though, before I launch you off. I kind of mentioned that the internet security relies on a problem that is in NP. So if you do find a way to keep everybody happy over Christmas, you will also have broken quite a lot of the internet. Most online shopping will just fail. Most financial transactions will not be safe anymore. So if you prove that p is equal to np, get in touch with me and then go hide somewhere until we can make sure that you're sufficiently protected. Most of us, sadly, believe that's not the case. We think it's the case that p is not equal to np. So what do you have to do to win $1 million that way? Well, to prove that, you need to show that some problem in NP doesn't have a polynomial time solution, right? That you can't solve it in any polynomial time. It doesn't need to be one of these hardest problems. It can be anything in NP. If you can show that something in NP can't be solved in polynomial time, then that thing is not in class P, and so class NP is not the same as class P. And so one of my favourite ones is graph isomorphism. So it's one thing to prove that you can solve it in quasi-polynomial time. It would be absolutely fascinating to prove that you can't do any better than quasi-polynomial time. And at that point, I will stop and wish you all good luck. Thank you.